Hello everyone, this is lecture 13, is on variation of parameters. So in this lecture, the focus is to talk about another solutions method to solve the particular solutions of the non-homogeneous differential equations. So in the last lecture, we talked about non-homogeneous differential equations where the general solutions consist of homogeneous solutions and particular solutions. And for particular solutions, we use method of undetermined coefficients to determine the particular solutions based on the right-hand side of the non-homogeneous differential equations. In this lecture, we're going to look at the method called variations of parameters, where we use this method to find the particular solutions for the non-homogeneous differential equations. The idea of using this variation of parameter is that sometimes the right-hand side of the non-homogeneous differential equation is complicated and this does not fall into some of the regular functions like exponential functions, polynomial functions, sine and cosine function, or the combinations of those functions. For instance, sometimes you have the right-hand side can be a tangent function, cotangent function, or secant or cosecant functions. Sometimes you have logarithmic functions. So those more complicated functions that present on the right-hand side of the non-homogeneous equations. When that is the case, the undetermined coefficients cannot be used to find a particular solution. So we have to move to another method. And the method again is variations of parameters. So for variations of parameters, the focus is on a very specific class of differential equations. Is actually the differential equation of this form, y double prime plus p of t times y prime plus q of t times y equal to g of t. Again, g of t is going to be different from 0. The difference between this type of differential equation and the one we considered in the last lecture is that a, or the leading coefficients of y double prime, has to be equal to 1. Okay. The procedure to solve for the particular solution is going to be presented in some example. For now, I want to talk about where's the formula coming from and why is the name variations of parameters. Okay, so if the function p, q, and g are continuous on an open interval I, and if the functions y1 and y2 are a fundamental set of solutions of the homogeneous equations of this form. So when you have the non-homogeneous differential equations, you're going to start out with finding the homogeneous solutions corresponding to the homogeneous equations. And then based on that, we're going to find out the particular solutions. For the case of undetermined coefficients, we make sure that we know the homogeneous solutions so that we avoid the linear dependencies of the particular solutions on the homogeneous solutions. But for variations of parameter, we do need the solutions y1 and y2 because the particular solution form does depend on y1 and y2. You will see in a minute. Again, I want to mention that the leading coefficient here, the coefficient of y double prime, has to be equal to 1. Now we're going to derive the particular solutions of the non-homogeneous differential equation by assuming that the particular solutions has the form of homogeneous solutions. So that is, the particular solutions is assumed to have the form y sub p equal to u1 of t times y1 of t plus u2 of t times y2 of t. Now for y1 and y2 are the solutions of the homogeneous equations. And u1 and u2 are functions that will be determined later. If you know y1 and y2, you can write down the homogeneous solutions, that is c1 times y1 plus c2 times y2. So we have been doing that already for a while now. So c1 times y1 plus c2 times y2. For c1 and c2 are some arbitrary constant. Now the idea for this method is that can you take this homogeneous solutions and apply that to the particular solutions? However, because again, we want to avoid the linear dependency on the homogeneous solutions, what you do is that instead of C1 and C2, those are constant, we're going to vary the value of C1 and C2. So instead of constant, now we choose a variable to attach to y1 and attach to y2. Therefore, the name variations of parameters. So we want to vary the parameters c1 and c2 and replace c1 by u1 of t and replace c2 by u2 of t, where y1 and y2 are the homogeneous solutions and u1 of t and u2 of t are functions that will be determined later. Okay, so that is the assumptions that we have to make, and assume this is a solutions to the non-homogeneous differential equations. That is, now we're going to find the first derivative, the second derivative, and substitute that into the non-homogeneous equations and solve for u1 and u2. Right. Then you have u sub b prime is equal to, so you take the derivative of these two terms, and remember they are products, and therefore you have to apply product rule. So taking the first derivative of this term, you have u1 prime, so I'm going to drop the t, times y1 plus u1 times y1 prime plus u2 prime times y2 plus u2 times y2 prime. At this step, I'm going to make another assumption, and the assumption is going to be very big, very useful for the calculations. Without these assumptions, the calculations become invisible to do. It's very tedious to do the calculations without these assumptions. So to make the calculations more visible, we assume that u1 prime times y1 plus u2 prime times y2 is equal to 0. Then you have that y sub b prime is equal to u1 times y1 prime plus u2 times y2 prime. Then we can move on to the second derivative of the particular solutions. Yp double prime is equal to u1 prime times y1 prime plus u1 times y1 double prime plus u2 prime times y2 prime plus u2 times y2 double prime. Then we're going to substitute y sub p prime, and y sub p double prime into the non-homogeneous equation. So substitute y sub p prime, and y sub p double prime into the differential equations or the non-homogeneous equations. We get that. So y double prime is u1 prime times y1 prime plus u1 times y1 double prime plus u2 prime times y2 prime plus u2 times y2 double prime plus p of t times y sub p prime, or u1 times y1 prime plus u2 times y2 prime plus q of t times y sub p, and the assumption for y sub p is over here. So that is u1 y1 plus u2 y2, and equal to the right hand side, which is g of t. So I'm going to move this to the left hand side a little bit. So this is equal to g of t. The next step is to distribute p of t and q of t, and we're going to use the fact that because y1 and y2 are solutions of the homogeneous equations, right? That is, when you substitute y1 and y2 into this equation, you get 0. So that's what we're going to do. So I distribute p of t and q of t. So we got u1 prime times y1 prime plus u1 times y1 double prime plus u2 prime times y2 prime plus u2 times y2 double prime plus p of t times u1 y1 prime plus p of t times u2 y2 prime plus q of t times u1 y1 plus q of t times u2 y2. This is equal to g of t. Now we're going to we're going to take u1 as the common factor and u2 as the common factor. And I see that we have u1 terms here. I have another u1 term here and u1 term here. I have u2 This is U2, this has U2 here. So U1 is a common factor, that is, and you're left with Y1 double prime plus P of t times Y1 prime plus Q of t times Y1. And U2 as a common factor, and you're left with Y2 double prime plus P of t times Y2 prime plus Q of t times Y2 plus U1 prime times Y1 prime plus U2 prime times Y2 prime equal to G of t. And again, as I mentioned earlier, y1 and y2 are the homogeneous solutions of the homogeneous equations. And therefore, when you substitute y1 into this equation, you get 0. And y2 into this equation, you get 0 as well. And therefore, we're going to see that this part or this expression is equal to 0. And this expression is also equal to 0. And you're left with just u1 prime times y1 prime plus u2 prime times y2 primes and equal to g of t. So this is one of the equations that we need to find the representations of u1 and u2. So the first equation that we see is from this assumptions earlier. That is u1 prime times y1 plus u2 prime times y2. And another equation is from here, u1 prime times y1 prime plus u2 prime times y2 prime equal to g of t. Okay. So we combine the equations. u1 prime times y1 prime plus u2 prime times y2 prime equal to g of t, and u1 prime times y1 plus u2 prime times y2 equal to 0. Then you get the following system of equations. So the system is, again, u1 prime times y1 plus u2 prime times y2 equal to 0. And u1 prime times y1 prime plus u2 prime times y2 prime equal to g of t. Okay. Now the next step is that we need to find the representations of u1 and u2. Okay. So either you can use substitutions or elimination method to solve for the solutions of the system, right? To solve for the representations for at least u1 prime and u2 prime. But what I'm going to do is that I'm going to turn the system of equations into a matrix vector form. So this is the knowledge that you have from linear algebra. Okay. So we're going to turn this into a matrix, the coefficients matrix of y1, y2, y1 prime, y2 prime, and what we're looking for is u1 prime, u2 prime, equal to the right hand side, that is 0, g of t. Okay. And to solve for u1 prime and u2 prime, we find the inverse of this matrix, of this 2 by 2 matrix. So assume that the determinant of this matrix has to be different from 0. If it's equal to 0, the matrix is non-invertible. That means you cannot find the inverse of this. So u1 prime, u2 prime is equal to the inverse of y1, y2, y1 prime, y2 prime, multiply with the right hand side, which is 0, g of t. And for the 2 by 2 matrix, the inverse of that is straightforward. It's going to be equal to 1 over y1 times y2 prime minus y1 prime times y2, multiply with another matrix, that is, you swap the place of the entry in the main diagonal. So y2 prime, this is y1, and put in the negative side for y2 and y1 prime. Then multiply with 0, g of t. Now, if you notice that the determinant of the determinant of the 2 by 2 matrix that we're talking about here is actually in the denominator. So that's why we have to make sure that the denominator is different from 0. And in a way, this is the calculation of the Wronskians that we talk about in lecture 8. Okay. Then you're going to combine, or you use matrix multiplication for these two matrices, and you're going to get 1 over y1, y2 prime minus y1 prime times y2. times the matrix, a new matrix here, that is y2 prime times 0 minus y2 times g of t. That's for the first entry. The second entry is y1 prime times 0 plus y1 times g of t. Okay, so I'm going to replace this part with the Wronskian. Therefore, u1 prime, u2 prime is equal to 1 over w of y1 comma y2 times the matrix negative y2 g of t and y1 g of t. This means u1 prime is equal to 1 over w, which is the Wronskian, times negative 2y times g of t, and u2 prime is equal to 1 over w times y1 times g of t. And to get the representations of u1, you just basically integrate both sides of this equation with respect to t. And to get the representations of u2, you just integrate both sides of this equation with respect to t, and you get the answer. So u1 is equal to negative of the integral of y2 times g of t divided by the Wronskian dt, and u2 is equal to the integral of y of t times g of t over the Wronskian with respect to t. Okay, so you get the representations of u1 and u2, and for w is the Wronskian, g of t is the right-hand side of the non-homogeneous differential equations, and y1 and y2 are the solutions of the homogeneous equations. Then we put everything together to write down the final form of the particular solutions. So the particular solutions is going to be of the form. So remember the assumptions that we have at the beginning, that the particular solution is u1 times y1 plus u2 times y2. So u1 times y1 indicates that you have negative y1 times the integral of y2 g of t over the Wronskian dt plus y2 times u2, which is the integral of y1 g of t over the Wronskian with respect to t. So this is the particular solutions in the case of non-homogeneous differential equations using the variations of parameter. So this is the formula that we're going to use, and in the calculation procedure, what you need to do is you need to calculate the Wronskians of the homogeneous solutions. Then use that to calculate the integral that give you the representations of u1 and u2, and then put everything together to find the particular solutions. And we're going to see the example later.